In this series of videos, we're going to study an extended application problem, the tank problem here. And what we're going to see is that even though this problem, which looks more like chemical engineering, has no obvious geometric interpretation to it, we're going to see that eigenvalues and eigenvectors are the critical tool we'll need to be able to predict the behavior of the system in the long term. So what is the system? We have two tanks that are full of water. They each hold 1,000 liters, and we'll call them tank X and tank Y. What's going to happen is we're going to be pumping water from one tank to the next. So we're going to take 100 liters out of this tank, put it into here, take 100 liters of this and put it into here. That maintains the volumes of water in both of them. But what's coming along with the water is a dissolved chemical. So often this is called a brine tank or a salt tank problem. The idea is that we have some particles in here, and there's not much in tank Y, but there's a lot in tank X. So if you imagine this as sort of muddiness or dirtiness in the water, we've got a fairly dirty tank here, a fairly clean tank here, and we're going to be engaging in mixing behaviors at specific rates. And what we're trying to do with that information is predict how much is going to be in each of the tanks over time into the future. And this is as the mixing occurs. So that's our goal, to predict. And what you'll find is that eigenvalues and eigenvectors are surprisingly common when it comes to prediction tasks. You'll also see similar tools in your second-year differential equation courses. Now, in terms of notation, we are going to work with just discrete times only. So we're going to have the 0th minute, the 1st minute, the 2nd minute, the 3rd minute, and so on. As a result, what we're going to see are series or sequences, and the notation we're going to use as a result is going to be things like x subscript n and not x of t. Now we need to get a little more particular about what that meant. Well, x sub n is going to be the mass of chemical Z in the tank X. So xn is how much of this chemical is in here, and it turns out it's easier to track all of this if we record amounts of the chemical rather than concentrations. Obviously they're related, but trust me when it's easier to model actual physical substances moving around when it comes to the modeling side. And having defined xn and yn, so how much is in tank X at minute n, how much is in tank Y at minute n, we can now see how we might have a vector showing up. If we partner these two elements together, they combine to define what we call the state of the system. If after 5 minutes we have 60 kilograms and 30 kilograms of chemical in each of those tanks, we could represent that with a vector form. Now we get to the actual modeling. We know how much we started with. So we have an initial state vector that says we have 80 kilograms of the chemical in tank X, and we have 20 kilograms of the chemical in tank Y. How do we go from this knowledge about the initial value of the amounts to what would happen 1 minute later or 2 minutes later? Well, this is what we're going to do on the next page. So what we can see from this diagram is that we're moving water between these two tanks, and with the water is going to come some of the chemical, but the amount's going to depend on the concentration. So it'll help us to know the concentrations in tank X. Well, it's the kilograms per 1,000 liters. So we have liters down here, we have kilograms up here, and the concentration in tank Y is going to be yn. And again, that's going to be in kilograms per liter. And so, after 1 minute, the amount of chemical, so this is now mass of chemical in tank X, well, that's going to equal xn plus 1. I'm going to put the equals there. xn plus 1 is how much chemical is in this tank 1 minute after we track these concentrations here. Well, how much are we going to have? Well, we're going to have 900 liters of tank X water, tank XN water, and it has a concentration, we just said, of xn over 1,000. And I will actually include all the units here so we can see how those cancel out in good chemistry terms. If we want to know how much chemical is in tank X after 1 minute of mixing, well, we're going to take the concentration we currently had in this tank and recognize that we're only keeping 900 liters of that, and we're taking 100 and moving it away. So we're going to have 900 liters that holds in each liter this concentration. But that's not all. We're also going to gain 100 liters carried from tank Y, and it's going to come with its own concentration. And kilograms here. So after 1 minute, we're going to have removed 100 liters out of the 1,000. So we're going to have 900 liters left of the original X water. And then we're going to have added 100 liters up here into our X tank. And it's going to be at the concentration coming from whatever the concentration in the Y tank was. So take a moment, think about that, look through the logic and go, okay, where's the stuff coming from? Do these units make sense? Absolutely. Our units cancel and we get kilograms, which is what XN represents. Think through that. And then it wouldn't hurt to try to predict what we're going to get for yn plus 1. See if you can reason through that. It'll obviously have parallels to what we just did. Okay, I'm just going to clean that up there. So for yn plus 1, we're going to have 900 liters left of the other tank, but I'm going to put it in the same order. We're going to have carried from X. We're going to have 100 liters at the previous X concentration. So we're going to take this blue region here and carry it over. And then we're going to have our 900 liters, this red region here, that is going to stay put. And we're going to have its concentration, kilograms. And so we can see the parallels here. We have, actually let's write this out in simplified form. If we tidy up all the constants, what we end up with here is 0.9 xn, and 100 over 1,000 is 1/10 or 0.1 yn. And for this one, it is similar in structure, except the 0.1 goes with the xn, and the 0.9 goes with the yn. And so what we're getting is, if you like a weighted average, the amount of chemical in tank X at the next time point is going to be mostly the previous concentration in the X tank, but there's going to be some influence from the Y tank because we're literally mixing the quantities. But here's also where we see our first matrix. If we imagine writing this out in vector form, remembering this is our state at the next time, we can get that using a matrix product with the current state. 0.9 and 0.1 are the coefficients for the first term, and for the YNs, the coefficients are 0.1 and 0.9. And so here we see our linear transformation. And so this is why we are interested in being able to model transformations even in contexts where we're not talking about vectors or geometry. Here we're talking about chemicals moving through a system, but the mathematics ends up being the same. We're now going to use that system to predict. This is the key thing for these mathematical models, being able to predict into the future what the level of chemicals is at the next few time points. So we know what we're starting at. So if we want to know the amount of chemical in both tanks at the next time point, 1 minute later, we know how we can calculate that. We put in our matrix, and then we include our initial conditions of 80 and 20, and we get a value back. This is our x naught here, and this is our y naught. And if we multiply this out, we're going to get 74 and 26 kilograms. So after 1 minute, there's 74 kilograms in this, down from 80. And in the second tank, tank Y, we started at 20 kilograms and we went up to 26. All right. Then just for the exercise here, we're going to keep going. It's going to be the same transformation matrix because all of the logic that went into building this didn't depend on the actual concentrations or the actual amounts currently there. It's just whatever they were, the next time point would come out of this calculation. So now we include our 74 and our 26. This is our y1 and x1. And if we multiply that out, your fingers, and you end up with 69.2 and 30.8. And again, that's kilograms. So we see as we mix, the 80 went down to 74, the 74 went down to 69.2 in this tank here. Meanwhile, the other tank is moving up. And finally, oops, this should be Y2, my apologies. And we can take it one further step just to get the flavor of the calculation. And we get this, so we put this matrix down here, this vector down here, do the same thing again one last time. Again, we could do this forever, but we're just doing a few to illustrate the process. That's going to give us, here I grab my calculator, I end up with 65.36, 34.64 kilograms. And with this observation, with this construction, we realize very quickly that what we want to be able to do mathematically is do powers. If we're asked to find an expression for the state after n minutes later, given the initial value, that's what we'd really like, right? It's easy enough. We have these values here. We started with x naught, y naught. And what we did is we just multiplied by the A matrix. We took this starting state and we multiplied by A to get x1, y1. And then we multiplied that by A to get x2, y2, and so on. And so if we multiply n times using matrix multiplication here, and sorry, this n times should go all the way out to all of our a's here, then what we're saying is xn, yn, the predicted level of chemical in both tanks into the future at any point is simply a to the power n times the initial values. And so in some sense, this is a perfect model. It's perfectly predictive, and we know how to do all these calculations. Whereas the obstacle come in, well, the complication is finding powers of A is tedious. Yeah, let's just go for tedious. It's straightforward. But if you want to get the 100th power of A, it's going to take you a while, and you have to do matrix multiplication at every step. Complicated or long matrix multiplication at each step. So we have a model for our system now. Going back to the pictures here, how does the chemical move through these tanks? We developed an updating for a minute-by-minute updating through the A matrix, and now we can use that to predict any point into the future. However, at the heart of that calculation is this a to the n calculation, which is complicated or long, and there's no way to generalize that nicely for a matrix like the one we have, unless we have another tool at our disposal. Enter the eigenvalues and eigenvectors.